So for introduction, the method of Lagrange multipliers have wide applicability in fields. Mainly, these methods are used in economics and physics. These multivariable optimization issues are more complicated since it can force limitation. The strategy of Lagrange multipliers is actually named after the mathematician Joseph Louis Lagrange, which he published this method in 1795. So, this theorem actually could also help mathematicians in solving many critical problems and also make most of the economies their work simpler. As in the real world, we already know that the application problem will use more than two variables and it is more complicated. So next for the key concept. Our key concept for this study is first a strategy for finding the local maxima and minima of a function subject to equality constraints. It is used for constraint optimization problems which involve several variables, which is more than two variables. The optimization problem is more maximizing or minimizing a few words relative to a few sets. Next, our objective. So the objective of our study, we have two objectives, which is first, to prove the Lagrange method can solve problems that more than two variables. Our second objective is to determine the local minima and maxima using constraints of Lagrange multipliers.
Okay, I will explain about methodology. In report, I explain three methods of Lagrange multiplier. The method of Lagrange is a strategy to find the local maxima and minima value of function f(x, y) subject to constant g(x, y) equal to k. This method is referred to two variable functions subject to a constraint. We just use x and y. As you can see, we will illustrate the problem by finding function f(x, y) equal to c. We are trying to maximize the function f subject to constant g. This means we are looking for a point x0 and y0. Figure 1 shows level of curve of function f equal to c. Each point intercept of g equal to 0. So the maximum value of f equal to 400. We conclude that fx equal to lambda gx, fy equal to lambda gy, and gxy equal to k. Okay, next, three variable functions subject to a constraint. This method to optimize the local minimum and maximum value of function f, x, y, z subject to constraint g, x, y, z equal to k. The constraint can be equation that describe the boundary of a region, or it may not be. The point x, y, z is restricted to lie on the surface S with equation g, x, y, z equal to k. Function f has an extreme value. T0 is the parameter value corresponding to the point P, and h has an extreme value at 0. So h point T0 equal to 0. In the term of component, the equation in x, y, z and lambda becomes fx equal to lambda gx, fy equal to lambda gy, fz equal to lambda gz, gxyz equal to k. This system of four equations in the four unknown x, y, z and lambda. Okay, the last method is three variable functions subject to two constraints. This method to optimize the local minimum and maximum value of function f, x, y, z subject to constraint g1, x, y, z equal to c, and g2, x, y, z equal to d. Thus, we are looking for extreme value. As you can see in the picture, if p, function p, x0, y0 and z0 is a point that produces an extremum of f when restricted to the curve of intersection of two level surface, then the gradient of f at x0, y0 and z0 will be perpendicular to the curve of intersection. The gradient of f at x0, y0, z0 is a linear combination of the gradient at g1 at x0, y0 and z0, and the gradient of g2 at x0, y0 and z0. Using the method for Lagrange multiplier, all we need to do is solve the following system of equation x, y, and z. We need to find delta f over delta x, delta f over delta y, and delta f over delta z. To find critical point function of x, y, f x and f z, f lambda and f mu equal to 0. In this case, that we have In this case, we have two Lagrange multiplier, lambda and mu, which may not need to be solved for in order to find point for which f contains extrema subject to the constraint of g and h.
So, to start this, for the first example of application by using the Lagrange multiplier method is through the simple pendulum. So, as we know, the pendulum can be defined as a particle travelling in 3-dimensional and its distance from a given point is fixed. So, by using Lagrange multiplier, the equations of the motion shows that the pendulum moves according to a superposition of forces which consists of gravity and the constraint forces which we call as F, and it is needed to keep the mass moving in a circle of radius. So this force is given by the terms of Lagrange multiplier in the motion equation. This is the example on how we solve the solution for simple pendulum. So consider the pendulum, it has a mass of m at the end of its string. The spring is laid out to be a straight line, which we can say that it is around a rod without a mass. And the length of the spring, we will consider it as L, and the spring should be L. So for the angle of the spring, we will assume it as theta. So, the simple Lagrange equation shows that L equals to half ml squared and degree of freedom squared plus mgl cos degree of freedom. So instead we use x equals to L and y equals to minus L cos degree of freedom. We will use f, q, I and t equals to 0. So after that, we will substitute the Lagrange multiplier with L plus lambda f. And lambda is the Lagrange multiplier. So we will assume that the qi symbol is independent and the lambda is another independent coordinate. So the terms of Lagrange multiplier can be interpreted as constraint force, which is F constraint equals to lambda df over dqi. And the constraint forces don't do the work. And to substitute this, we will get L equals to half m x squared plus y squared minus mgy plus lambda x squared plus y squared minus L squared. So finally, we will get L equals to half m, where r squared plus r squared degree of freedom minus mgl cos degree of freedom plus r minus L. So apart from that, we can conclude that the Lagrange multiplier that we use must be set to r equals to r equals to L. So the equation before is the final equation for using Lagrange multiplier. And that's all from me for the first application. Thank you.
Assalamualaikum and hi, my name is Fatin, Athirah, Iryanie, Binti, Roslan with metric number 264153. We'll be presenting example 2, which is application of Lagrange multipliers method to the power system economic operation. In this problem, the objective function is to minimize the generating cost, and the variable is subjected to the power balance of constraint. We are giving 3 generators with the following cost of function: serve a load of 952 minus watts. We have to calculate the optimal generation scheduling. F1, F2, and F3 are the 3 generators of the cost function. The first step in determining the optimal scheduling of the generators is to express the problem into the mathematical term, where we know F is equal to F1 plus F2 plus F3, while Gx must equal to 0. And now we have to set the mathematical term into the corresponding Lagrange function, which is capital Fx lambda equal to Fx minus lambda of Gx. And now we're setting lambda capital F equal to 0, and using partial differentiation for each function, we yield to this set of linear of equation. Now we solve for the set of linear equation into the Gx equal to 0, and we get the value for x1 equal to 112, x2 equal to 560, x3 equal to 280, and lambda is equal to 15. And we insert this value into the function of f, and we get the constraint cost is equal to $7,616 per hour, which is the minimum cost. This is generating scheduling that minimizes the hourly cost of production. The value of lambda is the incremental break-even cost of the production that gives the company a price cut for buying or selling the product or generation. Let's say if the company purchased the generation for less than lambda, then their overall cost will decrease. Likewise, if they sold for greater than lambda, their overall cost also will decrease, which we know that the optimal scheduling, which is lambda, is equal to 15 that satisfy to x1 and to the fx1 equal to fx2 plus equal to fx3, which gives the same value equal to 15. Since lambda is the incremental cost for the system, this point is also called equal incremental cost coefficient. Any deviation in generation from the equal incremental cost scheduling will result in an increase in the production cost of F. That's all from me. Thank you.
So for conclusion, we have clearly shown that the application of the method of Lagrange multiplier have been applied in physics and economics. So based on our study, this method has been used as a key concept in physics and economics, which for physics it refers to the movement of an object, and for the economics is for maximizing the profit subject of limited sources. The Lagrange multipliers method applied enable the firm to face and perform better in business and economic in future, and also could find the exact solution for a complex physics problem. So, in total, efficiency is said to be a helper tool which helps to save cost, time, and energy if we use it wisely.